Okay, so when n has this value 342, a somewhat large value of n, then we see that the proof that we have written down, we have two parts of the proof. Now, among those two parts, this part is useful for us for this particular value of n. Because n is even, this part is useful for us. But what about this part? For this part, the hypothesis that n is an odd integer, this hypothesis is false. So that means, according to the definition of implication, this part is vacuously true. So if instead of what we have done, while defining implication, that is, when x is false, we assume the implication to be true and it's called vacuously true. Instead of that, if we just define implication like this, if x is true, then this implication is said to be true when y is true, and is said to be false when y is false. And if that was all, then this part would become meaningless, this part of the proof. So unless we know beforehand the parity of n, that is whether n is even or odd, we cannot write a proof like this. Do you see my point? You may think that we have assumed n is an even integer, then this happens. And when n is an odd integer, then this happens. Then why is it false? We are assuming here that when n is an odd integer, then this happens. But look carefully, at any given time, since n is an integer, n cannot be both even and odd. So that means for some particular value of n, although n is a variable, but at a given time it takes one particular value and one only. Okay, so it is either even or odd. So while the whole proof is there, while both parts of the proof are there, at a given point of time or for a particular choice of n, one part of the proof becomes meaningless if we don't have vacuously true statements. Okay, so that's why vacuously true statements are needed. So you can see that it is rather convenient to have them, and using them you can write a proof like this without bothering whether the hypothesis is true or not. Otherwise what happens, every time in mathematics we come across this sort of thing only. We are given some hypothesis and we are asked to prove some conclusion. Although sometimes we also have if and only if statements. We have to prove both the ways. But anyways, we have to almost always deal with implication. So in that case, if your implication is defined unlike how we have defined, that is without having a scope for vacuous truth, then every time you state something like this, you have to assume beforehand that the hypothesis is true, and then you have to look for the conclusion. What happens when the hypothesis is false? That is not, this situation does not give any information about that. If your implication does not account for vacuously true statements. And similarly, if n is odd, so it can be odd also, because we are stating the result for every integer, not just even or odd integers, for any integer. So n can be odd also. In that case, this part of the proof becomes vacuously true, and this part of the proof is normally true. It's just true, not vacuously true. So if we don't have vacuous truth in our definition of implication, then this part becomes meaningless. So that's why we need vacuously true statements or vacuous truth, or that's why we need to define what happens when X is false. The hypothesis is false in an implication. Okay, so now from this theorem we can derive a corollary which is rather easy, and it will further emphasize the role played by vacuous truth. So look at this corollary. If n is equal to, I may take anything, I may take 151 plus 249 to the power 20,419 minus 241 to the power 50 plus 1, then n times n plus 1 is even. Okay. So if you are not convinced with what I have said just now about the role of vacuous truth in writing a proof, you will be convinced now. You see,